I can't find much information about the Schroeder S1 online, but it represents an era of innovation and interest in the mid-20th century where engineers were trying to find new and interesting ways to increase the performance and maneuverability of aircraft.
Imagine a world where traffic-clogged streets are replaced by silent, flying vehicles zooming overhead. What if your daily commute could take mere minutes, soaring above the chaos below? Cycloidal propellers, once a forgotten dream, could make this a reality. After decades of experimentation and failure, this revolutionary technology is now on the verge of changing everything.
However, its widespread adoption in military applications was somewhat restricted due to the war's demand and need for more mature technologies.
But it's not without its dark secrets. Cycloidal propellers, often referred to as cyclorotors, have a history that stretches back over a century, and yet they are still very much part of the conversation surrounding advanced propulsion systems today. The first concepts of cycloidal propellers appeared in the early 20th century, primarily through attempts to create more efficient ways of achieving vertical flight. Today, the same principles behind these early designs are being applied in the development of modern vertical takeoff and landing VTOL vehicles, as engineers aim to push the boundaries of aviation. At the heart of the fascination with cycloidal propellers is their ability to provide thrust in multiple directions, thanks to their unique design. Unlike conventional propellers that rotate around a fixed axis, cycloidal propellers use rotating aerofoils that move through a circular arc. This movement allows them to change the angle of attack quickly, shifting the direction of the force they generate. This adaptability makes them particularly attractive for applications requiring high maneuverability, such as VTOL aircraft, which need to move both vertically and horizontally with ease. The concept of the cycloidal propeller is not a recent one, though the earliest known design resembling a cycloidal propeller came from a Russian military engineer named E.P. Sverchkov, who introduced the Samolyot in 19. The vehicle featured paddle wheels for propulsion, a key characteristic of the early cyclorotor design. While Sverchkov's attempt did not achieve flight, it represented an important step in the development of cycloidal propellers, laying the groundwork for further research and innovation. In the 1930s, further advancements were made, particularly in Germany. One notable figure during this period was Adolf Rohrbach, whose work on the cycloidal propeller design gained attention in the aviation community. Rohrbach's design, which was evaluated by the German Research Institute for Aviation (DVL), was a significant attempt to apply the cycloidal concept to aviation. However, despite its potential, foreign aviation journals at the time expressed doubts about the practicality of the design, and consequently, funding for further development was not forthcoming. This setback would be one of many faced by the cycloidal propeller, as engineers worked to refine and perfect its design. In parallel with these aviation-focused developments, there were also attempts to apply the principles of cycloidal propulsion in other fields. One such example is the work of Jonathan Edward Caldwell, who designed a vehicle that featured rotating wings, intended to make the aircraft fly in a manner similar to a bird, specifically a goose. While this idea might sound absurd today, Caldwell's concept reflects the era's fascination with finding new ways to achieve flight. Unfortunately, Caldwell was later charged with fraud, and no working aircraft was ever produced from his design. Another interesting development during this period was the creation of the Schroeder S1 in 1930, a full-scale prototype that used a cyclorotor for forward thrust. This vehicle looked somewhat like a flying combine harvester and represented a unique design in the pursuit of better aircraft performance. Although not much information about the Schroeder S1 is available today, it serves as a reminder of the era's optimism and willingness to experiment with unconventional ideas. Despite the early failures, one success story did emerge in the maritime industry. The first operational application of cyclorotor technology came with the development of the Voith-Schneider propeller, VSP, a system that was designed for marine propulsion. Developed by Ernst Schneider and later enhanced by the company Voith, the VSP was successfully tested in 1937. This development marked a major milestone in the use of cycloidal propellers, but unlike previous designs, The VSP was not intended for aviation. It was aimed at improving the maneuverability of ships. The Voith-Schneider propeller was a significant innovation in marine engineering. Unlike traditional propellers, which only provide forward thrust, the VSP could generate thrust in multiple directions. This capability allowed vessels equipped with the VSP to move laterally, rotate on the spot, and adjust their thrust in any direction, offering a level of precision and control that was previously unheard of in maritime propulsion systems. The VSP proved to be especially useful for tugboats, ferries, and other vessels that required high maneuverability. The potential of the VSP was further recognized during World War II, when the need for nimble, highly maneuverable vessels became particularly evident. However, despite its capabilities, the VSP's adoption in military vessels was limited by the war's demands and the novelty of the technology. Nevertheless, the VSP found its place in the post-war era, particularly in civil maritime applications. Ports, harbors, and the growing offshore industry saw the VSP as a solution to the increasing complexity of their operations, leading to its widespread use in these sectors. In the decades that followed, Voith continued to refine and enhance the VSP. Advancements in materials science, hydrodynamics, and control systems led to significant improvements in performance and reliability. Today, the VSP is still used in a variety of maritime applications, including dynamic positioning systems for floating cranes and renewable energy systems, such as tidal and river current turbines. The VSP's success in the maritime industry demonstrated the effectiveness of cycloidal propulsion, proving that the technology could offer distinct advantages in terms of maneuverability, safety, and operational versatility. The transition of cycloidal propeller technology from maritime to aviation is a fascinating example of technological adaptation. While the basic principles remain the same, the application of cycloidal propellers in aviation requires significant adjustments to account for the differences between water and air. The lessons learned from the success of the Voith-Schneider propeller have undoubtedly influenced the ongoing efforts to apply cycloidal technology in vertical takeoff and landing (VTOL). Engineers are particularly excited by the promise of improved maneuverability and efficient thrust vectoring, features that could make VTOL aircraft more versatile and effective. Cycloidal propellers offer the unique ability to change the direction of thrust with ease, which could make them ideal for aircraft that need to perform complex maneuvers, such as hovering, vertical takeoff, and landing. The challenge, however, lies in adapting these systems for flight. Engineers must overcome numerous technical hurdles to ensure that the cycloidal propellers can function efficiently in the atmosphere, where factors like air density and speed differ significantly from those in water. Despite these challenges, the potential benefits of cycloidal propellers in aviation continue to inspire research and development. As we move forward, companies like Cyclotech, which are working to integrate cycloidal propellers into VTOL vehicles, are showing promising results. The basic concepts that were first explored in the early 20th century are now being repurposed and refined for a new generation of aircraft, potentially revolutionizing the way we think about air travel in the future. But before diving into the specifics of Cyclotech's work, it is important to first understand how these propellers operate and why they hold such promise in modern aviation. The operation of a cycloidal propeller, also known as a cyclorotor, relies on principles that are distinctly different from conventional propeller designs. In a typical propeller system, blades rotate around a fixed axis, generating thrust in a single direction. The cycloidal propeller, on the other hand, uses rotating aerofoils that move through a circular arc, creating a system that can generate thrust in multiple directions by altering the angle of attack of the blades. This design gives the cycloidal propeller unique advantages in terms of maneuverability and versatility, making it particularly well suited for applications such as vertical takeoff and landing VTOL vehicles and other highly mobile aircraft. The basic design of a cycloidal propeller consists of a number of aerofoils, which are arranged in a circular pattern around a central disc. These aerofoils are similar in shape to the blades of a conventional propeller, but they are mounted so that they can rotate through a circular path, creating a complex movement that allows the direction of thrust to change easily. The movement of the blades through the arc is key to the functionality of the cycloidal propeller, as it enables the system to shift the direction of thrust by simply adjusting the angle at which the blades meet the air. This ability to change the angle of attack in real time is what makes cycloidal propellers so appealing for applications that require precise control over movement. One of the core benefits of this system is the ability to generate lift or thrust in a typical propeller system. The tips of the blades move much faster than in a typical propeller system. The tips of the blades move much faster than intersections, which can create inconsistencies in the thrust produced. In a cycloidal propeller, however, all parts of the blade move at the same speed, meaning that the lift is distributed more evenly across this uniformity helps to reduce drag and increase efficiency, while also contributing to a quieter operation. When a cycloidal propeller is operating, the aerofoils are positioned at different angles depending on where they are in their circular motion. For example, when the goal is to generate vertical thrust, the leading edge of the aerofoil at the top of the arc will be positioned away from the center of rotation, while the leading edge of the aerofoil at the bottom of the arc will be pointed towards the center. This configuration creates a high-pressure difference between the upper and lower surfaces of the blades, resulting in upward thrust. Similarly, the angle of the blades can be to create thrust in other directions, such as downward or sideways, simply by changing the angle of attack of the aerofoils at different points in their rotation. In many cycloidal propeller systems, a mechanical linkage is used to control the angle of attack of all the blades simultaneously. This system ensures that each blade rotates at the correct angle as it moves through the circular arc, allowing for a consistent and predictable shift in thrust direction. A mechanical linkage system is relatively simple and allows for straightforward control, but it can also limit the flexibility and efficiency of the system. To overcome these limitations, modern cycloidal propeller designs often use individual servo motors to control each aerofoil independently. This more complex system offers greater flexibility and allows for finer control of the angle of attack, enabling the propeller to achieve higher efficiency and better performance. One of the major advantages of cycloidal propellers is their ability to change the direction of thrust quickly. Unlike traditional propellers, which produce a fixed thrust in a single direction, cycloidal propellers can generate thrust that is easily adjusted according to the needs of the aircraft. This thrust vectoring capability allows for highly precise maneuvering, making cycloidal propellers an attractive option for vehicles that require complex movement, such as VTOL aircraft. The ability to switch between vertical and horizontal thrust with ease could significantly improve the performance of future aircraft, allowing them to take off and land vertically while still being able to travel efficiently in horizontal flight. However, achieving this level of precision requires significant engineering. The angle of attack of the aerofoils must be carefully controlled, as even small adjustments can have a large impact on the direction of thrust. In addition, the blades of a cycloidal propeller must be able to withstand the stresses and forces generated by the high-speed rotation and the changes in direction of the thrust. This requires careful attention to the materials used in the construction of the propeller, as well as the design of the control systems that manage the movement of the blades. In many cases, the control of the blades is automated, with sensors and feedback systems used to continuously monitor the position and orientation of each aerofoil. This real-time adjustment allows the cycloidal propeller to maintain optimal performance under varying flight conditions. The use of advanced control systems can improve the overall efficiency of the propeller, ensuring that it delivers the right amount of thrust at the right time, regardless of the demands placed on the aircraft. The movement of the blades through their arc also has important implications for the efficiency and noise produced by the system. In conventional propellers, the tips of the blades move at much higher speeds than the inner portions, which can lead to the formation of vortices and the generation of significant noise. In a cycloidal propeller, because the entire blade moves at the same speed, the aerodynamic flow is more uniform, resulting in less turbulent flow and less noise. This reduction in noise could be particularly beneficial for applications where quiet operation is important, such as VTOL vehicles used in urban environments. The ability to produce thrust quietly while maintaining high maneuverability is one of the key advantages of the cycloidal propeller in these scenarios. While the benefits of cycloidal propellers are clear, there are also some technical challenges that must be addressed before they can be widely adopted. One of the main challenges lies in the control systems required to manage the movement of the blades. As mentioned earlier, the mechanical complexity of these systems can increase the cost and maintenance requirements, making cycloidal propellers more expensive and harder to maintain than conventional propellers. Additionally, the varying angles of attack and the dynamic nature of the blades can put significant stress on the propeller, potentially leading to wear and tear or failure under certain conditions. The stress on the blades is compounded by the fact that the rotor is essentially working against itself, trying to pull itself apart as it spins at high speed. These factors can increase the likelihood of mechanical failure, particularly in environments where the propeller is subjected to extreme forces. Another challenge is the size and weight of cycloidal propeller systems. Due to the need for large rotating aerofoils, these systems are typically much bigger and heavier than traditional propellers. This increase in size and weight can negatively impact the performance of the aircraft, particularly in situations where weight is a critical factor. While the thrust vectoring capabilities of cycloidal propellers can improve efficiency in some situations, the added weight can offset these advantages, leading to a lower thrust-to-weight ratio. This could make cycloidal propellers less suitable for certain applications, particularly where weight is a major consideration. Despite these challenges, engineers continue to work on improving the design and functionality of cycloidal propellers. The potential benefits they offer in terms of maneuverability, efficiency, and noise reduction make them an attractive option for a wide range of applications, from maritime vessels to aircraft. As technology continues to advance, it is likely that we will see further improvements in cycloidal propeller systems, overcoming some of the challenges that currently limit their widespread use. With ongoing research and development, cycloidal propellers could become a key technology in the future of aviation, particularly for vehicles that require high levels of maneuverability and efficient thrust vectoring. Cycloidal propellers offer numerous advantages over conventional propeller designs, but they are not without their challenges. The unique blade movement and the way they operate require a level of precision and complexity that can introduce both benefits and drawbacks. Understanding both the advantages and the difficulties involved in the use of cycloidal propellers is essential when evaluating their potential for widespread use in modern aviation, especially for vertical takeoff and landing VTOL aircraft and other innovative vehicles. One of the most significant advantages of cycloidal propellers is their ability to generate thrust in any direction. This thrust vectoring capability allows cycloidal propellers to change the direction of the force they produce quickly and with great precision. Traditional propellers, in contrast, are limited to providing thrust in a single direction. This means that any vehicle relying on a conventional propeller system must rely on a separate control mechanism, such as ailerons or rudders, to alter its flight path or direction. Cycloidal propellers, however, can perform all of these tasks by simply adjusting the angle of attack of the blades as they move through their circular arc. This unique feature allows for much more agile and responsive maneuvering, which is essential for vehicles like VTOL aircraft that need to take off and land vertically, while also being able to transition smoothly to forward flight. Another important benefit of cycloidal propellers is their quieter operation. Traditional propellers can generate significant noise, particularly at higher speeds, due to the fact that the tips of the blades move much faster than the inner portions. This difference in speed leads to the formation of vortices and turbulent airflow, which generates noise. Cycloidal propellers, by contrast, have blades that all move at the same speed. This means that the airflow around the blades is more uniform, reducing turbulence and in turn reducing noise. This quieter operation could be a major advantage for applications such as urban air mobility, where noise pollution is a concern. The ability to fly silently, or with minimal noise, could make cycloidal propellers a compelling option for future air taxis and other VTOL vehicles that will operate in densely populated areas. Cycloidal propellers also offer advantages in terms of efficiency. Because the blades move at the same speed throughout their rotation, the lift they generate is more evenly distributed across the entire length of the blade. In a conventional propeller system, the tips of the blades move faster than the inner sections, leading to a less efficient distribution of lift. This can result in higher drag and reduced overall efficiency. With cycloidal propellers, the uniform speed of the blades helps to minimize drag, improving efficiency and performance. This is particularly beneficial for aircraft that rely on efficient fuel consumption, such as electric vertical takeoff and landing eVTOL vehicles, which are expected to play a major role in the future of urban air mobility. However, despite these advantages, cycloidal propellers are not without their drawbacks. One of the primary challenges associated with cycloidal propellers is the complexity of the control systems required to operate them. Unlike conventional propellers, which have a simple rotational movement, cycloidal propellers require precise control of the angle of attack of each blade as it moves through its arc. This means that a sophisticated control mechanism is needed to manage the movement of the blades and adjust the direction of thrust. In many systems, this control is achieved through a mechanical linkage that adjusts the angle of attack of all the blades simultaneously. While this is a relatively simple and cost-effective solution, it limits the flexibility and efficiency of the system. More advanced designs, however, use individual servo motors to control each blade independently. This allows for greater flexibility and fine-tuned control over the thrust generated by the propeller. By independently adjusting the angle of attack of each blade, engineers can achieve greater efficiency and more precise control of the aircraft's movement. However, this added complexity increases the cost of the system and makes it more difficult to maintain. The increased number of moving parts also introduces the potential for mechanical failure, which can be problematic, especially in high-stress environments. Another challenge associated with cycloidal propellers is the stress placed on the blade during operation. Because the blades move through a circular arc and change their angle of attack constantly, they are subject to significant forces as they rotate at high speeds. This creates considerable stress on the propeller's structure, which can lead to wear and tear over time. The blades are essentially trying to pull themselves apart as they rotate, which can result in fatigue and eventual failure, if not carefully managed. This is one of the reasons why cycloidal propellers are often larger and heavier than conventional propellers. They require a more robust design to withstand the stresses generated during operation. This added weight can be a disadvantage, particularly in applications where weight is a critical factor, such as in VTOL aircraft, where the thrust-to-weight ratio plays a significant role in the overall performance of the vehicle. The increased size and weight of cycloidal propellers are also factors that need to be considered in terms of their practicality for certain applications. The large rotating blades required for cycloidal propellers make them more cumbersome and less efficient in terms of their thrust-to-weight ratio compared to traditional propellers. While the thrust vectoring capabilities of cycloidal propellers can improve maneuverability and efficiency in some scenarios, the added weight may offset these benefits, particularly in situations where weight is a critical factor. This could make cycloidal propellers less suitable for certain types of aircraft, particularly those designed for long-range or high-speed flight. Despite these challenges, there are ongoing efforts to improve cycloidal propeller systems and make them more practical for modern applications. Engineers are continuously working to enhance the materials used in the construction of cycloidal propellers, as well as to improve the control systems that manage the movement of the blades. Advances in materials science, such as the use of lightweight composites, can help reduce the weight of the propeller without compromising its strength and durability. Similarly, advancements in control systems,
such as the use of more sophisticated servo motors and electronic control, can improve the efficiency and reliability of cycloidal propellers. Furthermore, the development of more efficient electric motors and batteries could help mitigate some of the disadvantages associated with the size and weight of cycloidal propellers. As electric propulsion systems become more advanced, it is likely that we will see cycloidal propellers integrated into VTOL aircraft and other electric-powered vehicles. These systems will likely benefit from the efficiency gains provided by electric motors, helping to make cycloidal propellers a more viable option for urban air mobility and other advanced applications. The potential benefits of cycloidal propellers in terms of efficiency, maneuverability, and noise reduction make them an attractive option for future applications in aviation, particularly for V2A aircraft and urban air mobility solutions. However, the challenges associated with their complexity, weight, and cost will need to be addressed before they can be widely adopted. Engineers will continue to refine cycloidal propeller systems, working to overcome these obstacles and unlock their full potential. With ongoing advancements in technology, it is likely that cycloidal propellers will play an increasingly important role in the future of aviation, contributing to the development of more efficient, versatile, and quieter aircraft. Cyclotech, an Austrian company, has been at the forefront of advancing cycloidal propeller technology for over 15 years. Their focus is on adapting the principles of cycloidal propulsion, which has long been used in maritime applications, for use in vertical takeoff and landing (VTOL) aircraft. As the world increasingly looks to develop new forms of transportation, particularly in urban air mobility, Cyclotech's work represents a significant step forward in harnessing the benefits of cycloidal propellers for the aviation industry. The company's most prominent project involves a test vehicle designed to showcase the potential of cycloidal. This vehicle is a small, lightweight aircraft, weighing just 83 kilograms, with 4 cycloidal propellers attached to a carbon fiber chassis. The propellers are designed to spin at speeds of up to 3,100 revolutions per minute, and Cyclotech has already successfully demonstrated the vehicle's ability to fly indoors while tethered. This is a significant achievement, as it proves that the basic concept of cycloidal propulsion can be scaled for aviation, at least in controlled conditions. However, Cyclotech's ambitions go beyond indoor flight demonstrations. In 2023, after receiving approval from the European Union Aviation Techton, Cyclotech was able to demonstrate the vehicle flying outdoors. This was a key milestone, as it proved that the technology is not only viable, but also capable of functioning in real-world conditions. The demonstration showed that the vehicle could take off, hover, and transition between different flight modes using the cycloidal propellers. This marks an important step in the development of which should potentially revolutionize urban transportation by offering a more efficient, flexible, and environmentally friendly alternative to traditional modes of transport. Although these test flights have been a success, there are still many challenges to overcome before Cyclotech's technology can be. One of the biggest challenges is the issue of flight time. Currently, the cycloidal propeller-equipped vehicle's flight time is limited due to the weight of the system, particularly the batteries required to power the propellers. As with all electric aircraft, increasing the flight time requires the development of lighter, more energy-dense batteries, which is a significant technological hurdle. Despite this, Cyclotech's progress has been impressive, and their vehicle has demonstrated the potential for short-duration flights, which could be used for specific applications such as urban air taxis or other short-distance services. In terms of market competition, Cyclotech's work is not happening in isolation. Other companies, such as Jetson, have already developed their own eVTOL, including the Jetson 1, which also uses more traditional propulsion technologies. The Jetson 1, for example, has a similar weight to Cyclotech's test vehicle, but has a longer flight time of up to 20 minutes. The question then arises, will cycloidal propellers offer any significant advantages over more conventional propeller systems in the case of eVTOLs? Cyclotech's design offers the promise of increased maneuverability and the ability to change direction quickly, which could be a game changer in situations where precision is required, such as in urban environments, or when navigating around obstacles. However, it remains to be seen whether these advantages outweigh the challenges posed by the increased weight and complexity of the cycloidal propeller system. While Cyclotech's test vehicle is still far from being ready for commercial use, the progress made thus far highlights the significant potential of cycloidal propellers in the future of aviation. The technology is still in its early stages, but the ongoing work to refine the design and overcome the technical challenges could eventually lead to the development of efficient, scalable, and practical VTOL aircraft. These aircraft could play a crucial role in reshaping how we think about transportation, particularly in densely populated cities, where traditional ground transportation is often slow and inefficient. As the development of cycloidal propellers continues, it is important to keep in mind the broader context of urban air mobility. With the growing interest in flying cars and air taxis, it is clear that we are entering a new era of transportation. The ability to take off and land vertically opens up new possibilities for getting people and goods around in ways that were previously unimaginable. Cycloidal propellers, with their ability to provide precise control over thrust direction, could be an essential technology for these new vehicles, helping to make them more efficient, maneuverable, and suitable for urban environments. The future of cycloidal propellers in aviation will depend on continued innovation and the ability to overcome the challenges associated with flight time and system complexity. Cyclotech's ongoing efforts to refine their designs and scale their technology for commercial applications are a positive sign that this technology could play an important role in the future of urban air mobility. As the company continues to push the boundaries of what is possible, it will be exciting to see how cycloidal propellers evolve and whether they can provide a viable alternative to more conventional forms of propulsion in the aviation.